I am very happy to welcome you here during this virtual session of the ITC 2020. My name is Florian Wirtmüller, and today I will talk about our article entitled Towards Incorporating Contextual Knowledge into the Prediction of Driving Behavior. Let's start with the agenda for today. First of all, I will give you the motivation and show you the use driving behavior prediction approach. Afterwards, I will come to some performance evaluations and will finally show the context influence investigations. At the end of this talk, I will give you a short summary and an outlook on future research. So, what is contextual knowledge and why is it beneficial to incorporate it into driving behavior predictions? Okay, let's attack the first question. What is contextual knowledge? In general, it can mean all information on top of the vehicle kinematics of that vehicle whose behavior shall be predicted. Within this work, we introduce two terms to subdivide this information. On the one hand, we have what we call traffic situation context. This includes, for example, information about the objects and lane markings within the scene, like distances and speeds. These features can be characterized as highly dynamic and mostly continuous. When it comes to motion prediction, a lot of researchers model them as influence factors. On the other hand, they have what we call external conditions. This includes aspects such as weather, daytime, traffic density, or country. These aspects are quasi-static, mostly discrete, and apply to all vehicles in a given situation. How motion prediction systems are influenced by these aspects and how such information could be integrated into such systems is in contrast to the features on the left side not well investigated. So, let's come back to our second question. Why is it beneficial to incorporate contextual knowledge and especially knowledge about external conditions into driving behavior predictions? So, the simple answer would be we know that external conditions have an impact on driving behavior and therefore they have to be considered. For example, probably no one here will deny that he or she behaves differently while driving on an icy road or during bad visibility conditions. So most people will increase their safety distances to surrounding vehicles when being faced with such conditions. And exactly this effect has to be covered by motion prediction systems to enable safe and comfortable automated driving under all conditions. And as the simple answer is not enough, we wanted to demonstrate that our feeling here is right. So to do so, we adapted a known machine learning based motion prediction approach to the publicly available HIDE dataset and analyzed its performance under varying traffic densities. Some researchers investigated the impact of features such as weather conditions on the driving behavior. In contrast to them, we wanted to investigate the influence of external conditions on a known motion prediction system. So we first of all needed one. And here it is. The approach we used was firstly introduced in the below mentioned article in the IEEE Transactions on Intelligent Transportation Systems. It is constructed in a divide and conquer manner and produces probabilistic outputs. What that means is shown on the following slide. In a first stage, 3 maneuvers are defined. These are lane change to the left, lane change to the right, and lane following. A machine learning based lane change classifier estimates now the probabilities for the 3 maneuvers. This is here carried out as a simple multi-layer perceptron with a single hidden layer. In a second step, 3 position estimates are carried out, 1 for each maneuver. To do so, a so-called Gaussian mixture regression approach is used. This approach allows to estimate spatial probability densities rather than only one single shot estimate. Finally, the three position estimates are weighted with the calculated maneuver probabilities and added up. For further details, take a look in the original article. So, and as the original article was developed based on a dataset which is not publicly available, we decided to adapt the approach to the Heidi dataset from the RWTH Aachen. This dataset consists of 45,000 kilometers of highway driving and was recorded in 6 different highway sections in Germany using a drone-mounted camera system. To show how well the adaptation worked and to give you an idea of the system's performance during normal operations, we will now show a few performance metrics. First of all, we will take a look at the classification performance of a lane change classifier in the first stage. Therefore, we use the receiver operator characteristics showing that the two classes lane change to the left and to the right are nearly perfectly estimated. These are shown in red and green here. That the performance for the lane follow class drops significantly can be explained as samples belonging to that class could be confused with both other classes, whereas lane change to the left and to the right samples are that different from each other that they are normally not mixed up. Another interesting metric is shown here. Now we are investigating the median lateral prediction error over the prediction time against a reference solution using a constant velocity estimation, shown in blue, light blue, and a perfect classifier shown in dark blue. And our solution is shown in red. As the figure shows, our approach is nearly at all points in time very close to the solution with a perfect classifier and reaches a median lateral prediction error of less than 20 centimeters, also at a prediction horizon of 5 seconds. But let's now come to the core point of our investigations, the impact of external conditions on the prediction performance. To do so, we thought about influence factors for which it could be possible to perform the necessary investigations. Thereby, we came across the daytime, the day of the week, the weather conditions, and the location, and especially the country. All of these aspects were, according to different reasons shown on the slide, hard to investigate. Therefore, we selected the traffic density, which we found out to have two ultimate advantages. On the one hand, the traffic density can be calculated in a very stable way due to the vertical view onto the scene. In addition, it naturally covers other effects such as daytimes, in order of commuters or weekends. The traffic density, TD, is defined as number of vehicles, NV, per number of lanes, NL, and kilometers. But let's now come to our findings. What we see here is the median lateral prediction error at a prediction horizon of 5 seconds on the y-axis and the traffic density on the x-axis. The three curves which are shown correspond to the already introduced maneuver classes lane change to the left in red, lane change to right in green, and lane following in blue. As we can see here, the prediction errors for the lane change maneuvers are very noisy according to low data resolution. But nevertheless, both of these classes show the tendency to increase the prediction error while the traffic density increases as well. For the lane following class, the results are less noisy as the data resolution is much higher. In addition, the prediction error here decreases while the traffic density increases. This can be explained with two facts. On the one hand, the lateral oscillation human drivers normally conduct when following a highway lane has a smaller amplitude in the spatial area as the frequency is constant. On the other, the duration of lane changes increases while the traffic becomes more dense. Therefore, the position prediction problem becomes harder. Another figure substantiating this is shown here. Now we see the average lane change duration in black and the maximum lateral speed in yellow during lane changes as functions of the traffic density. As the figure indicates, the maximum lateral speed during lane changes tends to increase while the traffic density is also increasing. This means that one can imagine the procedure of a lane change during dense traffic as a long period of time where the driver slightly steers towards the lane marking and announces his lane change intention. Afterwards, the actual lane change is performed very abrupt and with a high maximum lateral speed, if a proper gap is reachable. In contrast, in light traffic, lane changes are performed slower and smoothly. Two situations illustrating this are shown on this next slide. As one can see in the top situation, the traffic density has a value of 9.75, which is a rather low value. The blue vehicle now performs a very smooth lane change with a duration of 8.08 seconds and a maximum lateral velocity of only 0.64 meter per second. In contrast to that, we see a situation with a rather larger traffic density of 12.69. In this situation, the regarded vehicle which performs a lane change is also shown in blue. As one can see from the trajectory and the values, the duration of a lane change is with 9.60 seconds significantly larger than in the above sample. In addition, the maximum lateral speed is also larger and reaches more than twice the value of the above situation. So, let's now come to a short summary and an outlook on further research. Within this article, we first of all differentiated clearly between the terms traffic situation context and external conditions. In addition, we adapted a known probabilistic motion prediction approach to the publicly available HID dataset and showed a great prediction performance with an area under the curve above 90-70% for all the maneuver classes in the maneuver classification problem. And in addition, we showed a median lateral position prediction error of only 18 centimeters and a prediction horizon of 5 seconds. Finally, we investigated the impact of the traffic density on the performance of the motion predictions. Therefore, we proved that such systems could significantly benefit from incorporating such information. In an upcoming work, we will present a fleet learning-based architectural concept enabling to collect large amounts of relevant data for context-aware motion prediction applications. This will be presented at the upcoming IEEE CIVTS. Further works will focus on using this data to improve the prediction performance during varying external conditions. Thank you very much.